Namaskaram everyone, welcome to this new video, and in this video we are going to continue our series of third person game. So in the last video we implemented the forward animation, as you all remember. Now it's time we take that into the next level by implementing advanced locomotion system, and that will also include strafing movements. Now, people who don't know what strafing is, so strafing basically allows the character to move sideways while still facing a specific direction. Now, this is a mechanic that is often seen in games with lock on combat systems. For example, when you lock onto an enemy in an action game or Souls game, your character moves left, right, forward, or backward while keeping their focus on the target. So, this is exactly the style of movement we will be implementing today. Also, in this video, I'm going to visually demonstrate and will explain how the locomotion directions and angles are going to play their role in this particular feature. So imagine this is our character at center. Okay, now this character is facing north, and before we go ahead, I want you to know that the locomotion direction is the direction your character is moving relative to where they are facing. Now, this is often calculated using the locomotion angle, which ranges from minus 180 degree to 180 degree. Now, let's break it down visually. Imagine this is your character facing in the forward direction, which is the north direction. We plot up two axes, x and y. Now, the north one represents the forward movement, the west represents the right, the south represents the backward movement, and the east side represents the left side movement. Now, the forward also means at a 0 degree, the backward represents minus 180 or 180 degree, or vice versa, I should say. The minus 90 degree represents the left movement, and the positive 90 degree represents the right movement. Now let's draw a line at an angle minus 45 degree and another line between 0 to positive 90 degree, that is 45 degree. Okay, now if your character's locomotion angle that is calculated by Unreal lies between minus 45 degree to 45 degree, that means this is a forward movement that we have to return from our logic. Okay, now we draw another line at positive 135 degree and another line at minus 135 degree. Now if our locomotion angle, again which is calculated by Unreal, is between minus 135 degree to 135 degree, we are supposed to return the backward movement. Now if it is not in this area as well, that means forward and backward is nullified, then it is either between minus 45 degree to minus 135 degree, or it is between positive 45 degree to positive 135 degree. If we just forget about the signs, if it's between 45 degree or 135 degree, that means it is either has to be in left or right. So we can judge it by the sign. If it is negative angle, that means it goes in the left direction, and if it is a positive angle, then it goes in the right direction. So this is exactly the ideal situation of the character moment. So we are in our game, and you can see when I'm rotating my mouse, the character is not rotating. So to fix this, we come out of the game mode, we go into the blueprint of our character, and we type rotation in the details, and we make this property true, that is use controller rotation yaw. So yaw is the rotation of the object around its vertical axis, controlling the left and the right movement. So if you now compile and play again, you can see the character is using the uh, controller's rotation. So when you move your mouse or rotate your mouse, the character is also rotating. Okay, So now this is done, and it's time we move into our animation blueprint. So go in characters, mannequins, animations. That's where we have our animation blueprint. So last time we just had this one animation. So instead of creating this sequence player node again and again, what we can do is go inside our Lyra animations and search for unarmed jog. Okay, so we have all the jogging animations. Let's just drag the backward, the right one, and also the left one. Okay, now we have, okay, we also replace this run forward animation with unarmed jog forward. Okay, all right, now what do we do is we double click on this and we ensure that force root lock and enable root motion is checked. Okay, and we press on save. We do same with this. All right, we do with the left as one. We do it for right one as well. Okay, our animations are lined up. Now we need to create a list where we can store the names of these animations, because we are not going to use these names, of course. So we are going to store the names of directions, and then whenever we uh, output or emit any one of those directions, the selected animation will be played. Okay, so to do that, if you are from programming background, you will find this very familiar, especially if you have done backend development. Go in blueprint. Under this you will find enumerations. Click on it and then name it e underscore locomotion directions. So this is a list of directions that we are going to create. So let's name our first direction forward, then we have backward, then we have a left, and we have a right. Right, now save it. Now this becomes a list, a type. Now whenever you give this type to any variable, that variable can only accept a value that is present in that list. Right, now we are going to add a node here, blend poses by enum, so that enum list is e underscore locomotions. So you can see it is having a default pose. We consider forward pose or animation as our default. Now we add other three by right clicking on top, and we correctly map them. So whenever we say backward, it plays this backward animation. If we say left, it plays this left animation. Now to correctly pick the animation, we are supposed to provide it enum value, and then let's say if we give 1, it will pick up this backward animation and it will start emitting the poses of this animation. So like I said before, we need to calculate locomotion direction every time, or I must say every tick. So we are going to need a variable, call it locomotion direction, and we press enter. Give it a type enum. Under this you will find your e underscore locomotion directions. So it is going to accept only the directions or the values that we have provided in this list. Press control, bring it here, connect it with this. Okay, now we need to update this locomotion direction so that it can output the correct animation poses. Now to calculate the locomotion direction, we are going to need the angle, the locomotion angle. So to calculate that, we need the character's velocity and its rotation in the world, arithmetic. So we need variables to store all these things so that we can use them in later stages. So go in blueprint thread function, and first let's create a function that will give us the velocity, and it will keep updating our variables. Right, so we give update velocity data. Now this function is called here, so let's bring this. Now every time acceleration is updated, then every time this thread safe update animation is called, it will update the acceleration, then it will update the velocity. So to update the velocity, we go here and let's add the property access node so that we can access our character movement component, and then you will find your velocity here. So the velocity all is in 3 dimensions, so this value is going to be a 3D representation of the velocity vector. So first let's set that. So to store it in a variable, just drag out a node and promote to variable, give the name character velocity. Okay, connect this with the execution pin. Now this is a 3 dimension, but we need 2 dimensional velocity for locomotion angle since our character is moving in x and y plane. So we are going to multiply it by a vector. So add a multiply node, make the x value 1, y value 1. So it's just like if it's 2 in all 3 directions, the x and y will be 2 and 2, but the z will become 0. Okay, so it nullifies the z value, and this way we will have our character velocity in 2 dimensions. So let's store this as well by clicking the variable character velocity 2D. Okay, and connect it with the execution pin. Alrighty, so we have the character's velocity in 3D and 2D. So let's also mark this function thread safe, otherwise it will not get called in this blueprint thread. Safe update animation, compile it. Okay. Alright. So we have the velocity. Now we need is the rotation. So we will create another function that will keep updating our rotation data. So for now we just need a rotation value. So to get the rotation, let's first add the property access node to again access stuff safely. Get search for get owning actor. Like I mentioned in the object hierarchy explanation, whenever you want to get lock rot scale, you access the get owning actor. So in this you will find the get actor rotation. So this is a rotator type, so we are going to store it, promote to a variable, call it character rotation. All right, so we have this. Okay, so now we have rotation and velocity both. So save it, mark it thread safe. Okay, now we need, okay, first let's drag it, connect it. So now first acceleration gets updated, then velocity, then rotation. Now it's time we update the locomotion data. So the locomotion data is consist of direction and angle in our case. So update locomotion data. Now the locomotion data has to be updated. So for that we need to calculate the locomotion angle. So for that we are going to bring the character velocity here. We're going to bring its rotation, and then we are going to connect it with a node called calculate direction. So this function is going to accept the base rotation and the velocity of the character, and it's going to output the locomotion angle. Promote another variable, call it locomotion angle, of course, and set it, connect it with your execution pin. Now it's time we decide to use our threshold. So if you are not using Lyra animations and using something else, you might need to tweak the values as per your convenience. But to do that, let's first just hit this compile and call this function in our blueprint thread safe update animation. So we call it here, connect it with this, hit save. Okay, it's not thread safe, I think. So let's just go to update locomotion data, call it thread safe, Save it, compile. All right, so we have our rotation, we have velocity, and then only after that we are going to calculate the locomotion data. Do not put this locomotion data before these two functions, because the velocity is updated, the rotation is updated, and then the locomotion angle will be calculated. So make sure to use the correct value, we update it first. All right, so we go to locomotion data function, and let's go close all of these tabs. So now to calculate the locomotion direction, we are going to utilize the threshold that we decided. So to store those thresholds, we need to create a type. So instead of creating 4 variables or 8 variables to store each single value, we are going to create a structure. So this is another type. Those from programming background will understand, but if you don't, then you can have a look here, or you can also search on web. So I will say structure of locomotion. I hope I spelled it correct. Locomotion direction config. So this is a type. Now we are going to, let's bring that image up. So now as per this image, we decided that if the angle is between -45 to +45, then we are going to go for the forward direction. So let's create 4 variables. So the minimum angle that we need for forward direction is -45. So let's create a field that can store this value. So we say forward min. Then we have maximum that we can accept, forward max. So if the value is between these two angles, then we say it's a forward movement. Otherwise, we check if it's between backward minimum and backward maximum. So like I told you in the intro video, the blueprint is built upon C++. So in C++, we have this structure type that allow us to create custom structures or custom types that can store multiple values. Okay, if you want to store single, just go for variable. If you have a bunch of values that you want to store together, you use the structure type. So okay, change these types to float because the values are float. Yeah, save it, close it, and now we have all set. We have our thresholds. So we are going to call it here. Now we are going to create an object from that struct. So we call make s underscore locomotion direction config. Now you can see I can put my 4 values here. So the minimum I was saying is -45, max is 45, backward min was -135, and this one is 135. Okay, so we have these 4 fields with us. Now we can pass it to a function that is going to calculate the locomotion direction. Okay, so let's create another function that calculate the locomotion direction for us. Okay, now this is a sort of utility function that will do our job. Okay, now, okay, will it go? Yeah, so let's bring our utility function here that is going to calculate this for us. Now this function is going to need this threshold map or object that we have created. So we will create input and write uh, thresholds, or let's say config. Yeah, so if you change its type to structure, just type s underscore locomotion direction config. Now it accepts a value of this type. So we have created this type value here. So we're just going to connect this here in. Now let's go into this. So we move it around. Okay, now you can split this structure pin and use these values, or instead what you can do is just right click here and search for get config. This will get your variable out as a node. Okay, all right, and we need a locomotion angle so that we can apply our checks. So where it is? Here you go. So it is getting difficult to find variables. After this part, we will just club them into their groups. So let's split this structure pin so that we can get these four values as a individual pin. Now we are going to emit this out, search for branch node. Right now we are going to check if this locomotion angle lies between forward min and forward max. So let's bring out the in range float. Now guys, remember this in range float is like a single axis. If we say minus 10 to 10, that means minus 10, minus 9, minus 8, and it goes up to the positive 10. So I will tell you where the confusion will happen when you are developing this logic. If this is between minus 45 to 45, we are going to return it first, and then we are going to say a return node. So return node allows us to return a value from a function whenever we want. So we add this here, we add a variable here. Let's call it direction and give it type e locomotion directions, and this would be forward. Now we are going to check if it is not in minus 45 to 45, then we are going to check whether it is between minus 135 to positive 135. So again, emit a branch node here. I'm going to duplicate this, control D. Now here's a catch. When you hold alt and remove these pins and connect this min and max, now this says minus 135 to 135. So this goes like minus 135, 134, and then up to positive 135. But actually we are checking minus 135, minus 136, like that. Okay, so we are going to revert the output of this. Okay, so we do not want between these range. So we use not boolean, we connect it here. Okay, let's go and say if it is not, then that means it's a backward movement. Add a node, say it backward. Now if it is not between minus 45 to 45, it's not even in the minus 135 to 135, then it means it is either left or right. So we check again by adding a branch node if the value of locomotion angle is less than 0 or not. If it is less than 0, then we say it's a left movement. So let's add a return node again and make it left. Duplicate it, add here, and plug it in and say it's a right. So if it is less than 0, we go for left. If it's not, which means it's greater than 0 or equal to, then we go for right. Okay, so we have beautified our graph. It looks good now. Everything is emitting something. Now we make this function thread safe so that it can be called in the thread safe function. Let's check over there. Now this finally will give us a direction, and that direction we have to update its value in this variable, which is locomotion direction. So plug this pin, output this value here, and bring it. Okay, so now we have everything ready. Now this is going to update the locomotion direction, and this blend poses will get the updated value every time, every tick. Okay, so now if I hit play, you can see if I press W, it's going forward. If I go S, it goes backward. If I do A, it's left. And if it is D, then it's right. But you can see when I try to move diagonal, it still performs the left animation sometimes. Sometimes it performs the forward animation. To fix this, first we need is something called as warping. So to enable warping, you go in edit and in plugins and you search for warping. So if this node is not enabled for you, just enable it. The editor will restart, and then you come back to this blueprint of our character. Now after enabling that, we will introduce two nodes that will help us. First is the leg IK, and the second one is the orient warping node. Okay, so let me explain you why we need the orientation warping node and the leg IK node. So when you saw that the movement, it was still performing the left and right animations when I was trying to go diagonal and sometimes forward as well. So basically, the leg IK node, the IK stands for inverse kinematics. So it is used to dynamically adjust the position of the character's feet relative to the ground. Okay, so let's just go here, remove this, and introduce a new node called leg IK. Okay, it's not gonna appear like this. Leg IK. Right now, if you will connect, you will see that there is a new node in between that converts the poses from local to component and back from component to local. Let's understand how this thing is working. See, leg IK works in a local space. All right. So there are two types of spaces in Unreal Engine. First is your local space. Second is your component space. Okay. So the component space is basically relative to the world, and the local space refers to the transformations relative to the parent bone of a given bone. So, for example, if I say the feet, okay, then they are relative to the leg bone. Now, when a leg IK adjusts the position of foot, the modifications happens relative to the leg bones. For example, thigh or pelvis. Okay, this ensures that the foot stays aligned correctly with the skeleton's natural structure. Now, leg IK often involves like rotation and translation adjustments that don't need to account for the entire character's position in the world. So, when it comes to the benefits of this local space, is that it it keeps the bone transformation constrained within the skeleton's hierarchy instead of the worlds. Okay, and also it avoids unnecessary calculation related to the world space, that means the component space. So if you select the leg IK, then you will see that there is a attribute called leg definition. Okay, now if you try to add a leg definition, you will see that it introduced uh, two bones, IK foot and FK foot bone. Now this stands for inverse kinematic foot bone, and this says forward kinematic foot bone. So if you search IK in the score, you will find all the inverse kinematic bones. So in this case, the inverse kinematic bone that we need is the left foot. Okay, and the forward kinematic is simply the foot, left foot. We need another for the right leg as well. So we will select the right inverse kinematic bone of the leg. So I will say IK foot R. All right. Now forward will be simple foot underscore R. This gives you the IK and FK bones of both the legs. All right. Now we will just collapse this. So we go back to the locomotion state machine, but let's hit compile first. Okay, and we go on walk cycle. All right, now let's have a look on this walk cycle. We introduce another node called orientation warping. Now if you just give it some space, add it in between, connect this to this and this to this. Okay, now there is a translation between the spaces. Before going into orientation warping, we go from local to component and then back from component to local. So we change this orientation warping mode from manual to graph. Now this allows us to put our locomotion angle. Let's bring it here and we plug it here. And this direction velocity would be the velocity we calculated in 2D. So we get this. This is nothing but coming from here, okay? So let's give it some space to breathe. Right. All right. So we have orientation warping with us. Now, if I just go and scroll and select this enable debug draw. Now you'll be able to relate to the graph that I explained in the start. Let's see what's the error here. um okay, so we didn't place the bones, the spine bones and the root bones. So let's understand this. The orientation warping and the locomotion angle operates in the component space. Now, locomotion angle is computed relative to the character's root component orientation, which is like in the world space. Okay, so now the locomotion angle directly determines how much to warp the animations. Okay, so component space is essential because these adjustments applied globally to ensure alignment with the desired movement direction. Okay, and the leg ik, which we just did, was something that works in the local space. All right, so I will just place the spine bones here by selecting 5. So if you search spine, you will see 1. Then select the second spine, then select the spine third, then select the spine 4, and then select the spine 5. We also need the IK foot root. Okay, and we also need the IK foot bones, which is nothing but the IK underscore foot left. Now, if your rig doesn't have, in case you are not following with the series and you are using some other rig, then you need to have those bones, otherwise the warping won't work. Now, compile it. Also, let's give some space to our character to walk in a very big plane. Let's select all this and delete and expand this by 1,000 and 1,000. Okay, and now we hit the play button. Now you can see you can see it is sometime it gets stuck. So to fix this, first of all we need to ensure that our loop animation is set to true for all these 3 players. Otherwise it will stop once this animation is finished. Now if you hit compile, play again, now if you see it keeps running. Yeah, you can see that drawing in bottom. You see that's what we draw on the presentation. It's 45 degree, and this is minus 45 degree. Then we have backward 180 degree, then it's 135, then it's 130 minus 135. Now I can see it adjusts itself by forward and the left animation, it warps. Now if I just escape it and remove this and directly plug into it without having the orientation warping and play it, so when it comes to the local space, the leg IK bone is adjusting itself, but you can see it is just sliding sometimes. So we need to fix that, and the way to fix that is by introducing the orientation warping node. Now if I compile and play, you can see the hips are changing their direction based on my angle. And if you try to rotate your mouse without releasing the keys, you can see how fast his hip is changing the direction. So to make it smoother, we can increase this blend time to 0.25, 0.25, 0.25, and 0.25. Okay, now if you hit compile again and if you play and just rotate your mouse, now you can see the movement of hip is slower than before and it is much smoother. Now if you increase it to, let's say, zero point 0.3 and now compile again, you will see that the animation is much smoother now. You can increase more, but that will introduce a slight more delay, which is sometimes not good. But it totally depends your animation, how are your animations. So blending time will be decided accordingly, and so the thresholds. Now you can disable this debug parameter by selecting this orient warping from here and compile it again, and it will disappear. All right, I think that's it for this video. I hope you liked this video. This was the locomotion that we wanted to implement along with the strafing movements. Now, in the next video, we will be introducing some new stuff. So please stay tuned. Do subscribe to the channel, hit like and share this with your friends. And do let me know if you have any kind of questions. And for the animations, you can check out the first episode. You will find the Google Drive link in the description. Okay. So till then, see you. Ta-da. Bye bye.